Hello everyone. Today we're going to be talking about the peak searching method of network screening, which is a topic we've covered briefly in CE 552, Traffic Safety, Operations and Maintenance here at Iowa State University. I am going to start off by touching on linear referencing because it's kind of a critical part of how we're going to apply the peak searching method. We'll do a peak searching overview and then we'll go through a little example on US 69 through Ames, Iowa. We're going to talk about how we determine what a route is. We're going to use the term route or corridor to mean the entire length of roadway that we wish to analyze. We're going to then talk about segments in terms of smaller portions of that roadway that will be split out for analysis. Subsections are then a smaller portion of the segments. And then now that you know how we're going to talk about the roadway once we split it up into smaller pieces, we're going to go over some calculations and talk about the results of our screening process. So a brief overview on linear referencing, we can think of a continuous stretch of roadway as being identified as a unique route. One of the most common examples that we see in transportation is an interstate. So if we were to think of Interstate 35 across the state of Iowa, we could consider that to be one route. Each route we can then talk about in terms of a beginning mile point, which will always be 0 when we're talking about a specific route, and then an end mile point, which is simply the mile point representing the overall length of the route. So if your route is 350.0 miles long, your end mile point will be 350.0. Using this linear referencing scheme, we can then identify the locations along the route of certain features or events such as crashes. For instance, if a crash occurred a half mile from the beginning mile point, then that crash occurred at mile point 0.5. When we talk about peak searching, we're going to talk about an iterative process. The first step of which is to split the corridor we're analyzing into segments. If we have a 5-mile long corridor, we might choose to split that corridor into 5 individual 1-mile segments. And then we could rank those segments based on the process that we're going to discuss. Before we get too far into our calculations, we want to set a limiting value for the coefficient of variation. Using the Highway Safety Manual default recommended value, we would use 0.5. Having identified our smaller segments from our longer corridor, we're going to want to split each of those segments into even smaller subsections. So our 5-mile corridor became 5 1-mile segments, and then each of our 1-mile segments would become 10.1-mile subsections. Once we've done all the splitting of our corridor, we can calculate the variance of the segment that we're analyzing. So we would perform this calculation 5 times if we have 5 1-mile segments. And the variance of the segment is just calculated by looking at the performance measure for each subsection versus the performance measure averaged across the entire segment, and then just divided by the number of subsections minus 1, just a simple formula for variance. When we're talking about performance measures, these could be a variety of things, but in the traffic safety realm, we're typically going to talk about crash rate or crash frequency. And what you'll see here is we're going to use a performance measure of crash frequency plus 1, and it's just due to some upcoming calculations in which the performance measure will be in the denominator, so we'll need to avoid 0 values. Once we've calculated the variance of each of the segments or the mile-long corridors in our hypothetical scenario, we need to go back and calculate the coefficient of variation for each subsection. The coefficient of variation is simply the square root of the variance of the segment divided by the performance measure value for the specific subsection of interest. Once we've calculated the coefficient of variation for each subsection, we're going to compare these values with the coefficient of variation limit that we set in the previous step. We want to look at, do any of our segments not have any subsections that have coefficients of variation that are less than that limit? If not, we need to look at increasing the length of the subsections in those specific segments. Then we're going to look at the performance measure that's associated with the minimum value for the CV subsection that does meet our coefficient of variation criteria, and we will use that value to compare one segment versus the other segments. Essentially what this is going to do is it's going to take the most hazardous or highest crash rate or frequency or whatever our chosen performance measure is, subsection, and assign that performance measure to the entire segment. And then we're going to do that for all of our segments, and then we can rank our segments separately. This figure just demonstrates the process of what we would do if none of the subsections of a given segment met our variance criteria. We would simply change the length and repeat that iterative process. Today, the example we're going to work with is going to be US 69 through the city of Ames, Iowa. And we can imagine this like the city of Ames has enough money to deploy safety improvements or countermeasures to a 1 mile section of US 69. So we want to identify which 1 mile section could use it most. Again, we talked briefly about our performance measure being average crash frequency plus 1 to prevent when we have to have the performance measure in the denominator of a calculation. We're talking about roadway segments here. I'm going to use the term crash frequency as crashes per mile. I understand that you could view that as being a rate, but since we're not specifically considering volume, I'm going to refer to it as crash frequency, at least on the segment level. Just for a little reference, the southern border of the city of Ames intersects US 69 at mile point 8.7, while the northern border intersects at mile point 15.1. So US 69 runs north and south throughout the entire duration of Story County, Iowa. And we can see here in the middle, at least in the middle of US 69, we have the city of Ames. And so we are going to focus our analysis on this. This goes back to the concept of trying to identify homogeneous segments for the sake of analysis. It wouldn't really be fair to compare US 69 through Ames, which is a primarily urban setting, to the northern and southern portions, which are primarily rural settings. This is just a close-up of the city of Ames, and we can see US 69 as it runs through the city. Just to get you familiar with our linear referencing scheme, these are the whole miles that occur on the route through the city. So you can see we talked about intersecting at approximately 8.7 and exiting at about 15.1. And these would be the various mile points. This is just for frame of reference. It's not critical to the analysis that we're going to conduct. Here you can see that I've split US 69 as it runs through Ames into mile-long segments, which I've named A, B, C, D, E, F, and G. Now you can look at G and realize that it's a little bit shorter than F. It's a half mile rather than the full mile. When we're performing peak searching, it's going to be a relatively frequent occurrence that our corridor that we're analyzing would not end on an even mile point. So to account for this, we actually overlap that last section. So segment G runs from here to about here. So G and F overlap for a half mile. Crashes that occur between at a mile point that's greater than 0.1 and less than or equal to 0.2 will all be associated to mile point 2. That's just for simplicity of naming the subsections rather than having to say this is subsection mile point 0.1 to 0.2. I'm just going to refer to it as 0.2. To perform the calculations, we've already gone over this part where we've identified our 1 mile chunks. We're going to use that limiting value recommended in the HSM for our coefficient of variation of 0.5. And then we've already split our roadway of interest into the 0.1 mile long subsections. So now we can get into performing some of the calculations. So the first thing is to calculate all of the crashes that occur at mile point 8.8. Once again, this is mile point crashes that are occurred at a mile point greater than 8.7 and less than or equal to 8.8. And then we're going to add 1 to that value again to avoid having 0 in the denominator of our calculations. Here, this would just be an Excel calculation where we take the performance measure, crashes per mile plus 1, and subtract the average performance measure for the segment that we're investigating and square it. And then we can calculate the coefficient of variation for that specific segment, which is going to equal this value divided by n minus 1, so in this case divided by 9. We'll take the square root of that and then divide by this performance measure, which would give us a value of 0.48. And I'm going to escape out of the presentation very quickly here, and we're going to look at an Excel spreadsheet that I've created to do these calculations. So again, this was the source of what we were just looking at in the PowerPoint slide. Here we're calculating the difference between the performance measure for a specific subsection minus the average of the performance measures for the segment and then squaring it. So when we look at cell G14, where we're looking at essentially our variance equation, and then we're taking the square root and dividing by the performance measure for the specific subsection that we're looking at. Then we're going to compare this value, 0.48, to the critical value of 0.5, and if it's less, we're going to consider this. We know we don't need to perform further analysis on this segment, and we can use this value and compare it against the other coefficients of variation for the segment, and then we'll determine which one is the lowest, and we'll use that. So here we see that this subsection for milepoint 8.8 has a critical or a coefficient of variation that's less than the limit value for the coefficient of variation. So we can possibly consider this. And the only other one that meets our coefficient of variation criteria is going to be milepoint 9. And we can see that milepoint 9 has a lower value than milepoint 8.8. So therefore, the coefficient of variation we're going to use for this segment is going to be 0.3. Now, what I've done here is I've copied over the crashes just to facilitate the use of a VLOOKUP command. So you can see here, I'm identifying that minimum value with just a minimum function in Excel. These values just copy over that performance measure. And then this value is a VLOOKUP that references our minimum coefficient of variation and compares it to column G, and where it finds the value in column G that matches, it grabs the associated performance measure and just puts it up here. And then for the sake of plotting, I've just copied that down for the entire length of the segment. And I've repeated this process for each of the segments that we've identified. And as you can see, essentially what we're going to notice is that the segments that have the highest crash frequency or the highest performance measure are the ones that we typically are going to rate the segment by. And that's true for all of the cases here. One thing we also notice is that for all of our segments, we have at least one subsection that meets our coefficient of variation criteria. So we don't have to increase the size of any of the subsections for any of the segments. Now we can go to this figure which I've made, which is simply plotting these values versus the mile point. And we can see that the most hazardous 1 mile long section, it occurs right here at approximately beginning at mile point 11.7 or so. And we can again confirm this with our table. So I said mile point 11.7, and we can recall that mile point 11.8 here extends from 11.7 and ends at mile point 11.8. So that makes sense. So then by these metrics, we would identify that road segment D with mile points greater than 11.7 and less than or equal to 12.7 is our most hazardous roadway segment. Just some notes on some Excel calculation issues that we might run into. And it's more so of trying to think about crashes, which are point events or point features, and road segments and subsections, which are line features, and looking at both of those in Excel. So the way we discussed for most of it today, even though I actually went back and kept repeating myself several times, was that we can discuss line features in terms of both beginning mile point and end mile point, or for simplicity, we can just pick one or the other, or even the midpoint as we had done in the sliding window method. And as long as we're consistent, it shouldn't be too much of a problem. Again, this is the figure that I had made. In the gray, we see the length of the road segment rated by the performance measure correlating to its most hazardous tenth of a mile, which is how we would perform the peak searching method. We can see if we were to plot the trend in crashes per mile per year, so we're looking at from each mile point a half mile in each direction, we can see that this kind of lags behind slightly what we're seeing with the highest point. But again, this is to do with the fact that we're ranking a stationary 1 mile segment based on its most hazardous tenth of a mile. So if the rest of the section was relatively had a relatively low number of crashes, it could potentially skew this result. So that's what we're seeing here. And then because I just wanted to plot using a line, we have a little overlap, but this just captures the overlap between our last two sections. And so if you have any further questions regarding the peak searching method, please feel free to email me. And if not, I'll see you in class.